Hi, everybody. My name is Tanner Acquisto. I'm a graduate student at Lamont. I work with NBASL. And for this work, I have a poster. It's poster number 1. I'll be showing you some updated results on 3D first arrival travel time tomography of the Alaska subduction zone using active source data acquired as part of the AACSE experiment, the Alaska Amphibious Community Seismic Experiment. This work is done with my advisor, NBASL, Pablo Canales at HUI, and Donna Shillington at NEU. So we've created with these active source data shown by these red lines over here, where we shot sound sources above a bunch of deployed OBSs. I'm showing you kind of the resulting 3D model here that I've created for P-wave velocities. I've got other things that we can kind of probe and look at, like along strike variations in the velocity structure here. That kind of spans, starting around Kodiak Island and then to the west towards the middle of the 70 segment. Yep.
Hi, everyone. My name is Sarah George. I'm interested in the role of the morphology of the seafloor when it subducts on the overriding plate. To address this, we went to the Peruvian flat slab, which is the largest active flat slab on Earth, and it corresponds with 2 subducting aseismic ridges, the Nazca Ridge and the fully subducted Inca Plateau. We looked at geomorphic indices, which show that places that interacted with the subducting ridges have younger channel morphologies. We also looked at thermochronology, which suggests similar, the timing of these processes also are younger in places where the ridges have passed by. We use this to argue that ridge subduction drives upper plate exhumation and changes in drainage networks. And we also think that there's sagging that occurs after these ridges pass by an area, and so that flat slabs are not equally flat along strike. This is actually out in EPSL already, although it says 2023, that's wrong. Thanks.
Hello, I'm Mahanama from SZ4D. So we have done a LG cube tomography study to get to know more about the lateral variations of attenuation in the crust of Alaska. So the main motivation behind of this study is the poor estimations of ground motion. Using the present ground motion models that we use for Alaska, we thought of having a better idea of the attenuations. That way we can adjust and get some better estimations for crustal attenuation. So we came up with a cube knot tomography that you can see in the left side figure, and also the frequency dependency as well. So the study is conducted for 5 frequency bands, 0.75 Hertz up to 12 Hertz. So anyone who is interested of knowing more about this attenuation structure, the lateral variations and all, please stop by at the presentation poster session. Thank you so much.
Okay, I'm reporting on 10 examples of the subductant interface that have been exhumed from the seismogenic zone. Oh, I'm Don Fisher from Penn State. And let's see, is this, and so if you use a flow law for diffusive mass transfer, which is what the microstructures show, the up-dip limit of seismicity is where you start to see visible strain in mudstones. The down dip limit is where you match the plate rate. And this, all that deformation is interseismic. It leads to a slip deficit. It can produce really large strains, and it has some predictions associated with the model, like there would be a tapering of the slip deficit with depth. Thank you.
Hello, party people. Thank you. I'm Jade Bowers, and we are some of the SC4 grads XCOM. So SC4 grads is subduction zones for graduate students and graduates, and that graduates is postdocs and non-faculty researchers less than 5 years from their terminal degree. And we're just up here to talk a little bit about, we care about mentorship for subduction zone scientists. We care about peer support, and really we're up here to highlight this skill building with SZ4D. This paper contains all of the times that I heard the things we want to do talked about in your talks, and it was more than 50% of the talks. We want to have workshops We want to help our junior scientists build skills. We also want to help our mid and late career scientists build these same skills. SZ4D is a big data problem, and we as geoscientists are not good with big data. So help us get these things going. That includes you working group members. Thank you.
Hello, everyone. I'm Tian Sang from the Geological Survey of Canada. And I'll bring this to share with you guys a recent application of Ocean Networks Canada's NEPTUNE cable system. And this is to monitor the 2021 magnitude 8.2 Alaska earthquake. And a special feature about ONC's NEPTUNE cable system is it has multiple nodes at different tectonic environments, from mid-ocean ridge to the accretion prism of the Cascadia subduction zone. And at each node, we have a little dense array of seafloor pressure sensors, typically co-located with broadband seismometers. And at the two nodes, we also have cork borehole instrument, which can measure pore pressure variations subsea floor. And cork was designed by my co-author Earl here in the year 1992. Over the past application, most application has been for geodetic purposes because of the low sampling rate running on the battery. But we are seeing some interesting in the seismic frequencies. And please check my poster. Thank you.
Hello, everyone. I'm Xiao Taoyang. I'm from Purdue University. You know, volcanoes have really diverse eruption behavior, some of which could be reviewed by seismicity. As shown here, we see a very clear spatial temporal migration of seismicity associated with the recent eruption at the Great Silicon volcano. So to understand how this migration of seismicity is controlled by the geometry and property of the magma plumbing system, we did an image of the velocity structure here showing on the lower left. We imaged the two low velocity zones in the crust, and those two low velocity zones are separated in spatially from the northwest into the southeast part of the island. And these two low velocity zones correspond to about 33% up to 33% melt, which are characteristics of a magma reservoir. And using the seismic velocity model combined with seismicity, we propose a 6-stage eruption cycle to explain the migration of seismicity. The findings in this study have broad applications to other volcanoes. Thank you.
Hello, I'm Leia Langer from USGS. This is our project on converted wave elastic reverse time migration imaging in subduction zone settings. The idea is to use converted phases to recover high resolution information about subducting slabs. So here we have a 2D synthetic structure, which is sort of similar to a subduction zone, and it's got a bunch of earthquakes underneath. And if I hit next, it should play, but we'll see if that works. No, it didn't. Okay. So what the movie would show you is that this is an earthquake. It's a shear source, produces shear waves that convert to P waves as they travel through the slab. Then we back propagate those. We record at 129 stations, back propagate in a smooth domain. We separate the wave field into the PNS components as we back propagate and cross correlate them. The cross correlation is bright at the locations of seismic discontinuities where converted waves were produced. And that's what you see in this image, is that we have successfully found the locations of the significant seismic discontinuities in the slab, and we can even infer the relative strengths. So if you want to hear more, talk to me.
Hi, I'm Joe Biasi, a postdoc at Dartmouth. Here's the idea. You measure the magnetic field at volcanoes, and as magma moves around, that magnetic field is going to change, so you can monitor a volcano that way. I have models that show that works. Test deployment at axial seamount that shows that works really well. It's very similar to gravity, but the advantage is that the cost of the instrument is much less. So you could buy one gravimeter, or you could buy 100 magnetometers for every SZ4D volcano, same price, right? And so with that kind of data and that kind of coverage, we can start to link magmatic changes to earthquakes or to landscape changes. You have a bigger picture, basically. That's all I got. Thank you.
Hello, I'm William Wilcock from the University of Washington, and the Ocean Observatory Initiative, which is an NSF facility, operates a sophisticated cabled observatory off Central Oregon. And the location of the portion on the margin off Newport was chosen to satisfy the needs of oceanographers, but fortuitously it lies in a region where there are big gradients in coupling, all located offshore, and there are also clusters of earthquakes that are hypothesized to be related to subducting seamounts. Currently, only 5 sites are instrumented for geophysics. So by instrumenting 3 more, shown by the red symbols, with seismometers and pressure gauges and a scientific junction box, which should enable more PI instruments, you could build a 5-node observatory offshore, which would be quite capable. And furthermore, there are 2 cables coming out of Pacific City to the north. And if you put permanent DAS on those, then you'd make the observatory even more capable. Thank you. And it's poster 63.
Hi, I'm Frederick Simons from Princeton University. I'm showing the poster made by Terry Shu, a graduate student, and worked on with myself and Bud Vincent and his team at DBV Technology in Rhode Island. We have built a underwater continuously operating reference system that works with a single station, autonomously surveyable system, whereby we can go very far in the open ocean, very deep, 6,000 meters, and for a very long time, for decades if we want. So we have built 4 of these systems and tried it on a real ship, but we are now in the process of surveying it with an autonomous surface vehicle made by Sea-Track. And so we think that this is one of the solutions that you'll want to take to Chile, Aleutians, or Alaska, or wherever else it's hurting. Thank you.
Hi, I'm Shangxin Liu, a postdoc researcher at the University of Florida. Here I'm showing the 3rd project of my doctoral study when I was in Virginia Tech. So we are using the very high we are using a very high dense linear seismic profile called Magic profile running from Western Ohio to the Eastern Virginia. We are trying to constrain the deep earth structure of the mantle transition zone below the eastern US Hasse margin. From our results, incorporating the 3D velocity correction, we find that both the deep earth 410 and also 666 structure, they both 2 interface become shadowing from the inland to the coast, which are hard to reconcile with any of the 3 previous hypotheses regarding the vertical mantle flow, which including A-driven convection, hydrosubpiling from the deep farland slab, and also the dripping, sinking, lithophile block from the delamination. So based on our new results, we propose a new deep earth vertical mantle flow hypothesis, which is relevant to the deep earth farland slab. We call the new mechanism called the hydrothermal upwelling mechanism. So if you want to know more about our results, please come to posters. Thank you.
I'm Terry Plank from the Lamont Doherty Earth Observatory, and I'm talking to you about the project AVERT, anticipating volcanic eruptions in real time. This is funded privately by the Moore Foundation, but it's designed to be a completely open project that is of benefit to the community, and we hope very much SZ4D. There are 3 novel aspects to our smart volcano sensor arrays. We actually just deployed them 2 months ago on Cleveland and Ocmok volcanoes in the Aleutians in full partnership with the Alaska Volcano Observatory. These are designed to be plug and play. You can add whatever equipment you want. We deployed a usual array of instruments, but also novel instruments like continuous magnetometers, soil temperature probes, and we have on-site single board computers that can actually manage the data flow and in the future actually conduct analysis on site, edge computing. We have smart power. It's all about power on an autonomous instrument. We have satellite telemetry, which is coming to Chile. And there's 2 new things that I want to point out. One is that we'll be having a workshop on novel data analysis, and we are going to be instrumenting a 3rd volcano. So come talk to me about it if you're interested in any of this. Thank you.
I'm Anne Bessel from Lamont, and I brought a poster that show very preliminary results from an active source data set that we just collected a few months ago with the Marcus Lang set off of the west coast of Mexico, where you have the young Cocos plate that is subducting underneath the North American plate. And for this experiment, we focus on the Guerrero seismic gap and the neighboring segment. Next slide, please. So this is a very interesting place to study because the Guerrero Gap has had an earthquake for about 100 years, but it ruptures very regularly in very large slow slip event, whereas the neighboring segment rupture regularly in magnitude greater than 7 earthquake. And next slide. So we don't understand very well this difference in megathrust slip behavior. So to investigate possible structural control on megathrust slip behavior, we collected multi-channel seismic data with a 15-kilometer long streamer and ocean bottom seismometer data. And on this poster, I show you preliminary images of the subduction zone and differences, very large differences along strike.
Hi, I'm Jeff McGuire from USGS, and I want to cheerlead a little bit for Southern Cascadia as a great place to work on the FEC question 1, particularly the interactions between locking on the megathrust and faulting in the overriding plate. I totally messed up and had a lot of animations that are now right on top of each other, but you can read a lot of the geologic features and sort of infrastructure things on the left that are really advantageous. But probably the thing that's less known is something called the California Middle Mile Initiative, which Cal Poly Humboldt is heavily involved in through their president's office at expanding fiber optic networks. And essentially every yellow highway that you can sort of see on the map on the right will very soon be covered with fiber optic cables that have potential dark fiber for seismic use. And we did a little pilot experiment with Cal Poly Humboldt this summer that went right across the most actively deforming faults in sort of the front of that section of orange faults under the Cal Poly Humboldt logo. And basically every little magnitude 2 earthquake scatters energy off the faults in the overriding plate and allows you to image it. And within about a year or so, there'll be something like 100,000 sensors right in the most actively deforming part of the overriding plate that could be used just to study lots of things. Thank you.
Hello, how's everybody doing? All right, I'm Dylan Ward from the University of Cincinnati. I've been working in northern Chile and the Chilean Andes on glacial related problems for about a decade now with people like Esteban Sagredo at Católica. One of the things that we've dealt with there is that in these volcanic mountain ranges, ash falls, pyroclastic flows, lava flows, landslide deposits, moraines, all follow gravity and they all end up in the same place and they're all bouldery messes. They all look really similar in the field and can actually look similar in map view. This confuses interpretations. Like if we want to understand whether mass wasting events are more common after glacier advances and retreats related to climate, or whether they're more common just in whether the background rate of these kinds of events in this earthquake-prone landscape, then we need methodology that includes modeling, remote sensing, and field work in order to try to improve the classification of these kinds of deposits that represent our archive going back older than the 10 years that SZ4D is going to be sitting around.
Hi, I'm Brett Carr at the University of Arizona. One of the more common types of volcanic activity you see at subduction zones is the effusive formation of lava domes. And these eruptions can last years, decades, and even some cases a century or more. One of the common patterns you see, this is data from Cenobong volcano in Indonesia, is when these domes grow, they are inherently unstable. And so these prolonged eruptions create a prolonged hazard for the people living in their vicinity. And so at Cenobong, we saw the eruption rate and the collapse frequency decreased over time, but the size of the potential collapse did not decrease. So as activity was declining, the hazard remained the same over the period of the eruption. In some case, and then many different processes cause instabilities in lava domes. And some of these processes correlate with eruption rate, so that eruption rate can be used as a proxy for collapse hazard. Other processes and also then the collapse size do not correlate with eruption rate. And so you need additional methods. We've been working on slope stability models to assess collapse hazard and potential collapse size. And so this just supports the need to fully assess this hazard. You need multiple data streams, and I'm excited for the opportunity at SZ4D to work with people studying magma transport pathways and also arc settings to get at the conditions that support these long-lived and support and drive these long-lived eruptions. Thank you.
Hi, I'm Jeremy from University of Houston. So in this study, we asked the question how different would magma looks like when they came from subduction zones with a range of subduction velocity. And to explore that topics, we look into two areas. One is the recent Tonga Kermadec, the long strike Tonga Kermadec introduction arc, and the other is the historical record in the Northeast Asia, like since a continental arc since 100 million years ago. And we use the statistical approach to correlate the convergence velocity with all kinds of magma geochemistry, and numerical modeling is also another approach that help us look into magma from slow and fast subduction. So the poster number is 65. Please come by if you're interested. Thank you.
Hi, I'm Gabe Epstein at University of Washington. The poster is presenting some new research merging geodynamic models extending from subduction initiation to maturity with thermodynamic models of metamorphic rocks to determine in-slab thermal structure as well as devolatilization patterns. So on the bottom left, well, on the bottom is a time series of these models. So on the left is the thermal evolution along the slab top with depth on the y-axis. The center figure is the within slab temperature difference at the surface and 5 kilometer depth of the slab, showing that this early subduction has a really important component of temperature variation. And then on the bottom right is the variation in devolatilization depth as you progress through subduction. But I'll highlight that while this is dependent on kind of from early to late subduction, it's also applicable to different along strike variability in subduction. Thanks.
Hi, I'm Yurong from Michigan State University. We are using MC method in this study to give like high attenuation anomaly in the backarc basin of Tonga subduction zone. This new result could actually update the left corner models provided by Jeff Faber's 2014. Our new result probably would give more malfraction than the maximum value that previous attenuation models would suggest, which is probably exciting. The second point is that, yeah, so because this is just preliminary result. The second point is that by combining attenuation and velocity, we could probably calculate the malfraction and distribution in such a complex spreading standard system. The third potential direction to go is by using such a unique technique, we could extend our model space into the mantle transition zone. So we could probably provide some clues about weather in the mantle transition zone. My poster is number 69, one of the last poster, and thank you so much.
Hello, everyone. I'm Valeria Cortez, and I really wish that you look at these figures and think, I can't read anything. So now, then you think, oh, now I really need to go to Valeria's poster to look at all the interesting features in this new reflection data. And when you're there, we can discuss about my hypothesis and the observation that we see of the possible relationship between different fork deformation and different megathrust behavior. I'm going to be there the first half of the time because all these lightning talks have been very inspiring, and I'm really going to go to those posters. Thank you.
Hi, everybody. I'm Will Hoover from the University of Washington. We know that the source regions of episodic tremor and slow slip are fluid rich, and these fluids can catalyze dramatic chemical changes. For example, the conversion of mantle wedge serpentinite to talc schist. Rheological modeling suggests that talc-rich rocks like these should be hosting slow slip, and we can go to the field to the exhumed rock record to test this hypothesis. In the middle there, we have a thin section image of a deforming talc schist. We see talc is nicely aligned and is accommodating deformation. But we also see on the far right that strong amphibole within this rock is heavily fractured, suggestive of high stress deformation. Best way we can explain this is with high strain rates in the talc rocks, and we propose that these high strain rates represent episodic slow slip events hosted by talc schist. So I think that's really exciting, and I also think this really nicely highlights the need to consider not only subduction zone inputs, but also the chemical reactions that produce new rocks within subduction zones if we want to get a realistic picture of how deformation occurs in subduction zones. And this also just came out in Geophysical Research Letters.
Hi, everyone. I'm Irene Pulaki at the University of Washington. This work is focusing on an exhumed subduction complex from southern Spain in the Beric Cordillera. And we are investigating the formational patterns that form in these rocks on the subduction interface, and then they're exhumed back on the surface. So by using geochronology, metamorphic petrology, and structural geology, we were able to build a pre-subduction stratigraphy, and then by that, investigate how these rocks were deformed on the subduction interface. So we see sediment slivers overthrusting on top of each other, similar to what geophysical studies have imaged in active subduction zones today. But by accessing the exhumed rock record, we can say which lithologies accommodate these slivers, what is the exact time of their formation, and what is their role during exhumation. So if you're interested to see how these duplexes look in the rock record, come by my poster. Thank you.
Hi, everyone. I'm Brandon Shuck from Lamont Doherty Earth Observatory, and this research is really focused on understanding faulting and deformation of the incoming oceanic lithosphere and understanding how that facilitates hydration of the oceanic plate, and then subsequently how do those fluids influence megathrust slip properties. So I've been working with active source seismic data collected by the Langseth last summer along the Cascadia margin, and specifically looking offshore Vancouver Island at the boundary between the Juan de Fuca and Explorer plates, where we have the developing Nootka fault zone. This is a very interesting transform fault boundary where there's a lot of elevated seismicity relative to the rest of the Cascadia margin. And our images show a really incredible about 40-kilometer wide fault zone with pervasive faults that go all the way from the seafloor through the sediments down to the crust and into the upper mantle, where we have reduced velocities that we think are indicative of enhanced fracturing and hydration of the oceanic lithosphere. And we think that these faults are acting as conduits for rising melts. As you can see, we have some seamounts and igneous intrusions here, and as well as other bright seismic anomalies with slow velocities that we think are trapped fluids and methane gas. So if you're interested, come see my poster. Thanks.
Hello, I'm Zach Spica, University of Michigan, and today I want just to give one message. What is the price of a mega DAS array? So what do you need if you want such array? Well, you need an interrogator. The best interrogator now, they can sample up to 100, 120 kilometers. You need to install the fiber offshore. That can be extremely expensive, an operation of several millions. And then you also need a very expensive cable. However, next slide. However, if you use already existing telecom infrastructure, then the price of the installation and the cable drop to zero. And so let's think about a mega array of an aperture of 400 kilometers. We would need like 4 interrogator and just go and plug them on one of the end of the cable inland. And we have a budget of less than $1 million to have the densest, largest seismic array that have never been installed so far.
Hello,
So in Chile, with the aim of supporting decisions about instrumentation and elaboration of volcanic hazard maps, we elaborated a ranking of Chilean volcanoes. So we evaluated 92 active volcanoes in terms of hazard and exposure, and they're very small. You see the result. Well, this is the available version, but we are working on an updated version that will be published next year.
Well, and those maps are showing the score for hazards in blue and exposure in red. As I hope you can see, there is a concentration of the darkest color, which means the highest scores are related, are located between 36 and 42 degrees in latitude. And from those comments, I would highlight that in spite that we have a effort collecting data for those systems, still there is a lack of information, mainly related to geological record and monitoring parameters. Thank you.
I'm not getting a second lightning talk. This is an announcement, but I did want to mention if you're interested in AVERT, not Lev is in the house too. This is about CIDR. Who's been involved in CIDR? Right, we've talked about it a bunch at this meeting. That's what it stands for. It's a summer program run out of Berkeley. It's been running for more than a decade. And we're going to have a new summer CIDR program in June. It will be in Berkeley, and the topic should be of interest to all of you. It's funded by GeoPrisms, but it's also forward-looking to SZ4D. You can see the themes there about faults and fluids, magma production rates, and magma transport at subduction zones and rifts. So lots of things to talk about. It's generally a 4-week program, involves all career stages with a focus on graduate students. Half the participants are early career. There's 2 weeks of lectures and tutorials. There's 2 weeks of research projects that are designed by the students, and it's massively interdisciplinary. So we will have a call for applying probably this fall or early January. So please apply. And Jeff Freimuller and Greg Hirth are also co-conveners, so you can talk to them about it as well. Thanks.
Hi, I'd like to thank the organizers or the conveners for this important and fascinating meeting. My name is Margaret Jadamak. I'm at the University of Buffalo. I'm building high resolution 3D models of subduction along the Pacific Ring of Fire. This is part of an NSF Career Award. The first hypothesis that the project's testing are that the volcanoes that are located off axis, so next to slabs, not above the slabs, that those are driven by 3-dimensional slab edge dynamics, and that is actually a common process in subduction zones. The second hypothesis is that as plate asthenosphere decoupling in subduction zones is controlled by nonlinear weakening due to the dislocation creep deformation mechanism, and that this weakening facilitates the slab edge volcanism. In terms of, and then in the right side, we see a plot of compute time, the size of biggest supercomputers worldwide through time, and then also their ability to perform floating point operations. So the takeaway, especially for the grad students, is that models like this can be done now with these advanced in computation. In terms of broader impacts, that bottom right, it's a clickable PDF, so you can click it, and then it links to zoomed in slab movies, and it's in Panopto, so you can use them in K through 12. And then also there's HPC modules that are being developed for the grad students, and you can see more about this in poster 27. Thank you.